Welcome. Today we start our discussion on Chapter 6, which is about probability distributions, and that is a topic that you have some prior knowledge of because you built one a couple weeks ago when we did the sum of two dice. Remember how we got that nice symmetrical histogram from our distribution because it was more likely for us to roll a 7 than it was for us to roll either 2 or 12. That's sort of where we're going to start today. The three types of probability distributions that we look at in this particular chapter are all discrete probability distributions. That means that discrete just means countable. That means that you'll be able to count the outcomes like 1, 2, 3, 4. We're going to take a look at this example to help us build our knowledge of probability distribution. So it says the best estimate of the percentage of all email that's spam is around 70%, and I would guesstimate that it's probably higher than that, but that's what we're going to use. Suppose it says you randomly select, random is important here, 3 email messages. Construct the probability distribution for the random variable x, and x is defined as the number of messages in our sample that are spam. So about 70%, they say. Let's get that up here. The probability of getting a spam message, I'm going to call that an S, is 0.7. And the probability of getting a not spam message, which is a good email, I'm going to call that N up here for not spam. That must be the rest of the time, which is 3/10. 70%, 30%. As you can see, we're going to build and fill in a table for this probability distribution where x is the number of spam messages ranging from 0 to 3, and p of x will be the probability for each of those outcomes. So let's start thinking about those outcomes. It's possible that we got no spam messages in our 3, which would be unusual but possible. So that would mean that on the first email we did not get spam, and on the second we did not get spam, and on the third we did not get spammed. If you heard all the ands in there, you'll remember that this should be a multiplication. These are independent events. The probability that the second message is spam doesn't change based on whether the first was or not. So we multiply probabilities for independent events, and that means that we should be thinking 0.3 times 0.3 times 0.3. That's going to be 0.027. We could have just one spam message, and that spam message could happen in the first email, but then the second two would be good. Or it could be that the first one was good, the second was spam, and the third was good. There's one more arrangement, and you can see what's happening. It's possible that we could get a good email the first and second times and spam on the third. All three of these possibilities have exactly one spam message. So we'll find a probability and then we'll multiply it by 3 because they'll all be the same. So let's see, we get one spam message, which is a 0.7. We get 2 good messages, which are 0.3s. And if you think about that, folks, those same numbers, they work here. 2 good messages, 1 spam, 2 good messages. Yeah, it's the same probability for all 3 of these particular outcomes. We're looking at all the possibilities about where that spam message could be located in our 3. 21 times 63. This is an 063. And we're going to need that 3 times. So when we get over here building our probabilities in the table, we're going to multiply that by 3. It's possible that we could get 2 spam messages, and those 2 spam messages could happen first and second. They could happen second and third. They could happen first and third. All 3 of these possibilities are going to have the same probability, and that will be 1 good message, which is a 0.3, times 2 spam messages, which is a 0.7. That probability will be 0.147, and if you think about that, again, there are 3 of that, so when we go to build our table, we're going to multiply that number by 3. There's only one more outcome that we haven't talked about, and that is that we get spam all 3 messages. The probability there would be 0.7 times itself 3 times, and that is 0.343. All right, let's go ahead and build our probability table here. The no spam, zero spam messages, that probability was 0.027. One spam message, we need 3 times 0.063, 0.189 that is. We have 3 combinations for things that would get us 2 spam messages. The probability that that happens one time is 0.147, but we have 3 items like that. That probability is 0.441. And finally, there was one outcome where all 3 messages were spam, and that probability was 0.343. Now, based on our knowledge of probability distributions, you should be able to add those up, and it should get to 1 or very close. Please pause the video, try it, add those up, and see what you get. I hope that when you added and got that sum, that came out to 1. Perfect. That's our probability distribution. Notice that this is very specific, based on a probability of success on one trial of 0.7. If the probability for getting a spam message is something other than 0.7, like maybe by the time you see this video it's up to 0.85, we'd have to do all this work over again to build that probability distribution, because our numbers would have changed. Our outcomes won't change, but their probabilities would have. So you can see that this probability distribution is very specific to this situation. However, this is a probability distribution, and there are some formulas for the mean and standard deviation of a generic probability distribution that always work. Notice we're using the symbol mu here. That's the capital mean. It stands for the population mean. Folks, in theory, right, we don't have any empirical data, not data we collected here. This is all about theory. And in theory, that's the population parameter. The standard deviation, we're showing the sigma here. Looks like an O with a curly Q on it. That's the lowercase sigma. There's the uppercase one. This is the lowercase one. So let's get you the formulas for those things. The formula for the mean, so mu, is equal to, and it's the sum of x, that is data value, times p of x. The probability that that happens. So for each of these rows in my table, if I want to come up with a mean for this distribution, I have to multiply the x value times its probability of happening. The variance of this distribution, you'll remember that the variance is the square of the standard deviation. That is equal to the sum of all the differences between x and x bar squared times their probability of happening. That means that, oops, that's the variance. If we want the standard deviation, we need to take the square root of all of that. So it will be the sum of, again, x minus x bar, distances from the mean, times their probability of happening. All right, let's move on and talk a little bit about this. Expected value is the same thing as the mean in a probability situation. If you think about that, expected value, it's kind of saying, yeah, what's the average thing that I should expect to get out of here? The expected value and the mean are the same thing, really. Take a look at this little situation. Suppose it says that the burglary rate for a suburban location is 23.2 burglaries per 1,000 households. If we've got a house located here, what should an insurance company charge for $5,000 worth of burglary insurance in order to break even? Well, a break-even price is where the amount that they charge for the policy is the same as the amount that they expect to pay out on it. So I think we could find that. If you think about it, we have a probability that somebody gets broken into, so a probability of a burglary, 23.2 per 1,000, that's 0.0232. The probability then that they don't get broken into, and I'm going to make that be my n, is 1 minus that, 0.0232, and that is 0.9768. Let's take a look at this situation, and maybe it'll help us a little bit to organize our thinking. Really, the question is, do you have a break-in, yes or no? So I'm going to put that break-in, a yes and a no. Those are the two options. And what our X value is, okay, is the amount of payout that you're going to get in either situation. X, and I'm going to put right under there, payout. Well, if there's a burglary, you're going to get $5,000, because that's what it's talking about right there. If there's not a burglary, you get nothing. Well, that makes pretty good sense. Now we can talk about the probability that X happens, the probability that the company has to make a payout. And according to what we were given, that probability is 0.0232. The probability that they don't have to pay out anything is much higher, 0.9768. And to find the expected value, what they should charge to break even, that's the mean of this probability distribution. So we need to have our mean is going to be the sum of X times P of X. So let's just think about that quickly. X, P of X, 5,000.0232 is 116, and well, this is easy. 0 times that is still 0. That means that our XPXs, the sum of those, are 116, and the break-even cost of a policy ought to be $116. Now, you know and I know that the insurance company is going to charge you more than that because they don't want to just break even, they want to make money. The manager of a hardware store has come up with this probability distribution, which you can see is missing a little something. Let's read the situation here. He's renting steam cleaners on Saturday, and if he rents one for 3 hours, that's a $30 income for him. If he rents it for a full day, $50. So you get a little bit of a bargain if you're the customer there. Or if he gets lucky, right, he can rent it out twice for 3 hours, and that will make him $60. The probabilities that are showing here, they do not add up to 1. So we definitely are missing something, and that something would be no rentals, right? If that's the truth, then there will be no cost for him. He won't get any money from it, and that will happen 0.7, 0.2, or 20% of the time. We are asked to find the expected rental income. Folks, that's the mean. So we're going to find the mean, and we're also going to find the standard deviation. The mean in this situation is going to be the sum of all the XPXs. So let's think about that real quickly. XPX, 30 times 0.4 is $12. 50 times 0.3 is going to be $15. 60 times 0.1 is going to be $6. And 0 times 0.2 is going to be 0. Now our mean is going to be the sum of those things. So 12 and 6 is 18, and 15 more is $33. So his expected rental income on any typical day is around $33. Finding the standard deviation, the formula for standard deviation, you'll recall, is it's the sum of X minus X bar, or data value minus average squared, times the probability of X happening. Do those little calculations for this situation, only 4 of them, so I think that we will not use our calculator, although of course we could do this in the lists of our calculator. But if the average is 30, then here's what we got to think about. We need the standard or the square root of all of this. It's going to be 30 minus 33 squared times 0.4 plus, because we're summing these up. The next one will be 50 minus 33, and I'm going to just write the 17 here. 17 squared times its probability, 0.3, plus, and now it's the difference between 60 and 33. That's 27. squared times 0.1. And the last one, the difference between the data value and the mean would be negative 33. 0 minus 33 squared times 0.2. All right, why don't you pause your video for a second, go ahead and do that calculation, and I will too. I came up with the square root of $381, which is around $19.52. Very good. I mentioned just in passing that you could do this in your calculator. If you were going to do that, the rental costs would go in list 1, the probabilities in list 2, and you can find the mean and standard deviation the same way that you did before with one variable, stat. I'll write that here. 1 var stat, and it's L1, comma L2. Okay, data values in list 1, frequencies or probabilities in list 2. So, all right, I think that's it for me today, and we'll talk more about this in class tomorrow. Have a good night.